Welcome back to Mechanical Engineering Made Simple. Today we're doing a deep dive for a listener grappling with, well, arguably the most frustrating question in engineering. Why is my system overheating when the calculations say it shouldn't?
Oh, absolutely. It's that deep chasm between theory and reality, isn't it?
It really is.
And we've got a fantastic stack of sources for this one. We're covering everything from, microscale thermal properties and chip
All
packages.
the way up to the mechanics of these massive industrial heat exchangers.
Right. And our mission today is really to understand why our perfect, clean theoretical calculations so often just collapse in the face of real-world messiness.
Okay, let's unpack this. We are tackling 5 key mysteries that seem to plague every thermal designer. Why our textbook constants are often wrong. Why systems might melt down at startup. And how to find that single limiting factor, the true thermal bottleneck in any design.
We're getting past the textbook and into the actual science of system failure.
So we all know the routine.
Yeah.
You run the numbers.
Mm-hmm. You use the standard material properties, you plug in the constants,
Right.
and then you watch the prototype fail its thermal stress test. You calculate a certain temperature, and the actual reading is 20 degrees higher. What did we miss?
Well, the calculations are only as good as the boundary conditions you define. And maybe more importantly, they're only as good as the hidden thermal resistances you just assume away.
Okay, that's where it gets really interesting.
When we talk about overall thermal resistance, R sub T, we often think of it as a simple series path. Hot fluid, wall, cold fluid.
Right.
But even for a basic heat exchanger, the heat has to fight through as many as 5 resistances. You've got convection on the hot side, conduction through the wall, convection on the cold side.
And you're saying there's more.
Yes, plus the fouling or buildup on both the hot and the cold surfaces.
And I imagine even simpler systems have their own hidden complexities. They do. Take a microprocessor package. The overall resistance, R sub T, is the sum of the fundamental one-dimensional resistance, R1D, and this other thing called spreading resistance, R sub sp.
Wait, what exactly is spreading resistance for our listeners? Is that just the heat fanning out from the source?
Precisely. If you have a tiny, powerful heat source, like a microchip, and it's attached to a larger piece of metal, like a heatsink base, the heat has to spread out laterally to use the full surface area of that heatsink. R sub sp quantifies the inefficiency of that lateral heat spread. If you don't account for it, you think your heatsink is working a lot harder than it actually is.
That makes perfect sense. So let's talk about the absolute king of overlooked thermal resistance.
Contact resistance, R sub co.
Exactly. This is so frequently underestimated, especially in mechanical joints that aren't, say, metallurgically bonded.
This is critical in industrial applications. Just think about tubular heat exchangers. You have one fluid flowing through a tube, another flowing outside. If those tubes are simply expanded into the tube sheets,
Creating what's called an interference fit.
right. If you do that, you absolutely must anticipate significant bond or contact resistance. That mechanical interference is great for a pressure seal, but thermally, it's just terrible.
If you braze them instead.
If those components are braced together, you're creating a true metallurgical bond. Then, for all practical purposes, you can neglect R sub co entirely. You have a continuous flow path for the heat. If you don't braze, you're just relying on these microscopic, imperfect point contacts.
So it sounds like what wrecks our big macroscopic models is this friction at the microscopic level. We assume 2 surfaces are touching perfectly, but they're not.
They absolutely are not. For 2 rough, non-conforming solids pressed together, the complex joint resistance, R sub J, is actually 2 resistances working in parallel. You have the actual metal-to-metal microcontact resistance.
RIIC.
And you also have the microgap resistance, RI-NA. The microgap is literally the air or the fluid that's trapped between the rough peaks of the 2 surfaces.
And if you're operating in a vacuum, say in a space application, those microgaps contain nothing.
A vacuum contact. Which means that R-my-G value just skyrockets because there's no interstitial substance, no air, no grease to carry heat across the gap. You're entirely dependent on those few metal-to-metal contacts. This is why engineers stress so much over minute surface roughness standards.
Okay, so if R sub co is so critical, what's a classic real-world scenario where an engineer missed this and, well, paid for it?
The most common one I see is in thermal management for high-power LEDs or power electronics. A designer specifies a certain thermal paste, the interstitial substance, for the joint between the component and the heatsink. But then on the assembly line, they run out of the expensive stuff and swap it for a cheap, high-viscosity gap filler with terrible thermal conductivity.
So the bond is fine mechanically, but the R-sub code just explodes.
It explodes, and the component starts burning out prematurely. The calculation was perfect. The assembly reality was completely flawed.
Now, let's tackle that other classic problem. Why does a prototype work perfectly in the lab, but then fail out in the field?
This raises a really important question. Are your test conditions actually matching reality? The specs for high-performance chips, for instance, often assume something like a 45 degrees Celsius ambient temperature.
Which is hot, but it's a controlled environment.
Exactly. But if the field environment where that equipment is installed is hotter, say 60 degrees Celsius, inside a tiny, unventilated telecom enclosure, your design immediately fails its thermal requirement.
And then, of course, things get dirty over time, which was never an issue in the pristine lab test.
That is fouling. It's the progressive accumulation of heat-insulating substances on surfaces. Fouling is an insidious thermal killer because it adds resistance slowly over time.
So if you design a heat exchanger for a constant load, but forget to account for this gradual insulation,
you eventually lose performance. It's guaranteed. The Tubular Exchanger Manufacturers Association, TEMA, provides guidelines for this. They define specific fouling factors for common fluids.
like what?
Well, for heavy fuel oil, TEMA says you have to factor in a resistance of 5.3 to 12.3. If that resistance isn't built into your initial calculation, field failure is just inevitable down the line.
We also need to think about bigger design flaws, right? Things that create pockets of insulating material like non-condensable gases.
Indeed. This is a common and a fascinating failure mode in large power plant surface condensers, especially those with radial vapor flow into a tube bundle.
How does that work?
When steam condenses, it shrinks, and the non-condensable air that was initially dissolved in it just gets left behind. If the design is poor, pockets of this gas form.
And those pockets act like insulation, blocking the steam from reaching the cooling tubes.
Exactly. A good tube bundle layout has to be meticulous. It requires that the pressure drop from the top of the bundle all the way down to the air vent manifold is identical for all possible vapor paths. That way you ensure a continuous sweep of those gases out of the system.
Okay, so we've covered the solid side resistances, both static and fouling, but often the true variable we need to nail down is on the fluid side. Specifically, that heat transfer coefficient, H. We know the textbook values are fantasy, so how do we find the one we should actually use?
What's fascinating here is that we really need to move beyond those simple correlations. We all remember from school, Nusselt equals C times Reynolds to the N times Prandtl to the M.
Equals CER to the M.
Got it.
Real.
Right. Those are great for a basic understanding, but they assume conditions that, well, they rarely exist in the real world.
Yeah.
You have to truly understand the flow regime and the geometry.
Right, because the textbook Nusselt numbers, like 3.66 for laminar flow in a round tube, that only applies when the velocity and temperature profiles are fully developed.
Meaning the fluid has settled into its final behavior pattern, both mechanically and thermally. But in reality, every process starts at an entrance, and that entrance region changes everything.
So the heat transfer coefficient is higher at the start because the fluid near the wall is still cold.
Much higher. And that thermal development length, X sub T, is the key we so often miss. In certain thermally developing flows, especially when the Prandtl number, PR, is much greater than 1.
Which means the fluid's thermal boundary layer is thin compared to its velocity boundary layer.
Right. In those cases, that thermal entrance length, X sub T, can be way greater than the physical flow development length.
So the velocity profile might settle down quickly, but the temperature profile keeps changing deep into the system.
Exactly. The fluid is moving at a stable velocity, but it's still busy absorbing heat for a much longer distance than you thought. If you ignore this entrance region, you massively underestimate the heat transfer coefficient you need for the device.
And how do we quantify that length?
We can approximate the thermal entrance length, X sub T, by taking 10 to the minus 2 times the Prandtl number times the hydraulic diameter D sub H times the Reynolds number Re sub DH. The big implication is that if you have a high Prandtl fluid, like oil, your thermal development zone is huge.
And the textbook coefficient just won't apply until much, much farther downstream.
Exactly, and if you introduce phase change, say condensation or boiling, those simple correlations don't just bend, they completely break.
Right.
In flow boiling and condensation inside tubes, the heat transfer model has to account for the flow pattern itself. Whether it's annular, stratified, slug, or mist flow, The physics are wildly different.
And the predictive correlations are different for each one.
Wildly different. You might have a correlation that's perfect for annular flow, where you have liquid in a ring and vapor in the middle. But if your system briefly operates in a slug flow regime where plugs of liquid block the tube,
That correlation is suddenly useless.
totally useless. It's a detective game just to choose the starting equation. You have to know your flow pattern.
Now, for that classic mystery we mentioned, why does equipment spike in temperature at startup and then just stabilize? Feels like the system is getting used to the load.
What you're seeing are the effects of thermal mass and transient behavior. It's transient versus steady-state blindness. If a solid has high thermal conductivity and no external cooling, the initial temperature rise rate is constant. We described that with the lumped capacity solution.
Which relates the change in temperature over time to the internal heating rate,
Yep.
Q, and the mass-specific heat product, M times C sub P.
Correct. So the initial concentrated heat input rapidly raises the temperature of the heat source itself, that tiny high-power element, before the larger surrounding structure, the thermal flywheel, can respond and spread the heat out.
Oh, okay.
Thermal modeling of integrated circuit packages is actually classified into 4 distinct time intervals after you apply power. First is the early period, where heating is confined entirely to the chip.
Okay.
Second, the intermediate period, where the die bond and encapsulant get involved. Third, the quasi-steady period, when the entire package begins responding. And finally, you reach the steady-state period.
So that initial temperature spike is confined to those early periods before the full thermal mass of the package can even catch up.
Exactly. And the takeaway for our listener is that if your temperature sensor is placed right next to the heat source, you will capture that sharp, scary spike. If it's far away on the casing, you might miss it entirely and only see the gradual quasi-steady rise. Sensor placement determines which reality you measure.
And the startup change could also be fluid dynamics related too, couldn't it? As things heat up, the fluid properties change.
Absolutely. If the fluid in your heat exchanger starts cold, its viscosity is higher. That higher viscosity means increased resistance to flow, which can decrease the flow rate and the heat transfer coefficient, leading to that initial overheating. It all stabilizes as the control system responds and the fluid temperature normalizes.
So it's this complex interplay between the component's thermal inertia and the fluid's properties changing dynamically.
It is. So if we connect this to the bigger picture, successful thermal management is often about just identifying the weakest link, the thermal bottleneck in that entire resistance chain.
Right. The total thermal resistance is the sum of all the individual parts.
Yeah.
Convection, conduction, fouling. But which one is the problem?
And this brings us to a crucial design question. How do you know if conduction or convection is the limiting factor? And, more importantly, when is adding fins completely pointless?
That's the million-dollar question for a lot of engineers.
It is. Extended surfaces, or fins, are primarily effective only when the convective heat transfer coefficient, H, is low. Fins exist to dramatically increase the surface area when the environment, the air, or the fluid is just not good at pulling heat away.
But if the material side, the internal conduction resistance, L over K, is already the bottleneck because the thermal conductivity, K, of the material is poor,
then adding fins is utterly pointless. The heat can't even get efficiently from the base of the fin out to its tip.
So if you have a massive aluminum radiator trying to cool something but the material is bad, you have a conduction-limited problem. More fins just means more metal that the heat can't even reach.
Exactly. We measure this with something called fin efficiency, eta. For an optimal design, you usually want that efficiency to be between 0.5 and 0.7. If your calculated efficiency is, say, 0.2, that means 80% of your fin surface is barely contributing.
You need to focus on the material conductivity, not adding more surface area.
Precisely. And conversely, think about plate fin heat exchangers, where one fluid, like a liquid, has a huge heat transfer coefficient compared to the other, like air. In that case, it is entirely permissible to have no extended surface in the core on the liquid side.
Why add metal when the fluid is already doing an excellent job of pulling the heat away?
Exactly. The convection resistance is negligible there, so the entire design focuses on boosting the air side.
So what does this all mean? How do we use this knowledge to design better systems from the very start?
The ultimate goal should be something called entropy generation minimization, or EGM. This is the philosophy that says you have to design systems that minimize waste and irreversibility.
And this is different from a standard exergy analysis.
It is, because EGM specifically forces you to adjust the physical characteristics of the design, the geometry, the materials, the finite dimensions. to minimize that irreversibility, not just rely on general thermodynamic parameters.
So EGM sounds like the process of finding the optimal compromise between flow resistance and heat transfer surface area?
It is precisely that balance. For systems cooled by forced convection channels, like microchannels in a chip cooler, an optimal channel size, D, exists. This is where EGM shines.
Okay.
If D is too large, your total heat transfer surface area is too small and the walls overheat. But if D is too small, the flow resistance is incredibly high, requiring huge pumping power and causing friction that can overheat the entire volume. EGM helps you locate that sweet spot.
We started this deep dive with 5 common points of failure in thermal design, and what we found is that every problem really boils down to correcting a flawed initial assumption.
Right. Underestimating contact resistance, ignoring transient startup behavior, applying correlations outside their applicable flow regime.
Or just failing to factor in environmental variables like fouling.
The jump from that simple textbook equation, Q equals UA delta T, to a robust real-world design requires recognizing that physical reality like fouling over time, or the geometry of microscopic contacts, always introduces resistance that our ideal models neglect.
So successful mechanical engineering is minimizing the destruction of exergy, quantified as T naught multiplied by S-gen, that's introduced by all these real-world constraints.
Exactly.
That sets us up for the future then.
Yeah.
The highest heat fluxes forecasted for high-performance computer chips back in 2006 were about 30.7 watts per centimeter squared. Given the relentless trend toward miniaturization and power density today, how do the complexities of microscale heat transfer, where effects are governed by electron and phonon interactions and continuum models, start to break down? How does that challenge the basic principles we discussed today?
It forces us to rethink everything we thought we knew about thermal resistance.
That was a seriously deep dive into the world of thermal physics. Thank you for providing the sources for this exploration. And you, our listener, if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.